a network. Network is a directed graph with V being a set of vertices and E being a set of edges. So yeah, and also we have a value called Q. Qij is a capacity of directed edge from I to j. So let's draw some network.
Попробуй червоний маркер.
Better?
Так краще думаю.
This. Yeah. So in the network we have two special vertices. One called source, and we mark it with letter S, and one called sink. We mark it with letter T. So the main problem with networks is finding a flaw. So let's think of this network as a system of something like pipes, and the flaw is water, and the capacity is amount of water that can flow through the pipe in some time. So what we want to know is how much water we can put through this network, starting in source and ending in sink in some amount of time. So mathematically, we define flow, valid flow, as a set of numbers Cij, such as Cij less or equal than capacity. So we can't pass more than capacity flow than pipe has. Yeah, so the other property is for every vertex that is not sink and not source, we should have that the sum of all flows coming into a vertex is the same as the sum of all flows outcoming from vertex. Yeah, so it's like simple. And the last constraint is for...
let's try to take a task closer. Maybe it will be better.
Can see anything?
Let's check.
Maybe blue.
Oh, now it's better, I think.
Yeah.
Let's take it left. I think more left. Okay.
Yeah, so the last constraint is for the source. We only have outcoming flow. So let's write down that sum of flows outcoming from source should be equal to some value V. And for the sink, we have only flows that coming to sink. So let's take a look at the sum of flow coming to sink. It should be the same value V as the flow that is coming from source. Yeah, because we don't have any like vertex in this network. that are generating more water. So what we have at the start is what we have at the finish. So the max flow problem is a problem that maximizes this value v. And this value v is called the value of the flow in network. Yeah. So now let's actually see how can we compute this max flow. So let's take a look at the theorem called max flow min cut equivalency. So what is min cut? Min cut is another term, and it represents the minimum set of edges, the set of edges with minimum value that are needed to separate the source from sink in network. So as we see in this network, we can cut through edges, through these two edges. And now we will have a source separated from sink. Yeah, so now let's try to prove the theorem that min cut value is the same as max flow value. Yeah, so min cut basically divides the network into two sets of vertices. Let's mark them as XO and X tilde O. Yeah. So at first, let's show that max flow can't be larger than min cut. So we always have our vertex S inside of XO and our vertex T inside of X tilde O. So every chain that are going from S to T should contain an edge that connects XO and X tilde O. But all of these edges are inside of min cut. So we can't push more flow through these edges than min cut. Thus, we can't push more flow than min cut in network at all. Yeah, so it's pretty obvious. So the next step is to show that we, in every graph, we can construct such a flow that its value will be at least min cut. So let's show actually an algorithm how to achieve this. So the first step is to assume that XO contains only vertex S. Now we'll be building something called augmenting chains. Yeah, so basically what we do next, if we have some vertex xi inside of XO, then for each xj where we can push more flow through this edge, so Cij is less than Qij. That's if we consider direct edges. But we also have something called reverse edges. Yeah, so if we at some point consider that we don't want to push that much flow over this edge, then we want to push, we actually want to push some flow through reverse edge, like to compensate the shot. So at the start, the capacity of this edge is 0. But if we push, let's say we pushed one flow through this edge, then capacity of reverse edge became also 1. So another constraint will be word.
Я буду знімати тут брати покраще. Можеш виключити камеру тут. Ти сказав, що будеш показувати. Я думаю, вони мене чують.
Yeah, so the second constraint will be if this is a reverse edge, so we should have that Cij is more than 0 if ij reverse. Yeah, if these constraints are met, then we can add xj to xo and move again to this step, but with xj instead of xi. So at the end, when we cannot add anything, we will end up with two cases. So the first case is when t is at xo. So d is inside of our augmental chain. So in this case, we basically found some way in the network where we can push more flow. Yeah, so we always can push more than one because here we have strict inequalities. Value that is equal to minimum of uij minus cij for straight edges and minimum of cij for reverse edges. Yep. So that's the value that we can push at each step. It is always greater than 1. And the second property is that we won't violate our constraints at any time. So because we won't set the flow through reverse edges less than 0, and because of this, we won't set the flow through straight edges more than capacity. So what we actually do when we push this flow, we just go over our augmented chain, and we just increase Cij for each edge that we see. Yeah. And the second case is when we don't have our sink in augmenting chain, and that means that we actually just finished constructing a flow. Yeah, so this is the end. Basically, it's called the algorithm of Ford-Fulkerson, and it works in asymptotics of big flow value multiplied by E. Yeah, so the only thing that we can say about the complexity of this algorithm is that at each step we increase the flow at least for one, and each step takes E operations because we basically do something like DFS or DFS. Yeah, so the complexity is flow multiplied by E, and that's suboptimal because we don't know nothing about the flow value in network before we compute it. Yeah, so let's see how can we optimize this approach. So the first optimization will be called Adam's card. Algorithm. Yeah, and what the Adam's card algorithm does, it runs. It's basically the same as Fort Halverson, but instead of DFS, it runs BFS at every step. And if we remember the condition that we written down before for the value of flow that we are passing, then we can see that at least one edge in graph will have Cij equal to QAG. Let's call such edge saturated. Yeah. So the another thing that we can see is that the edge can become saturated again only when we see it in BFS further than it was when we saw it before it was saturated before. Yeah, so like the average chain in BFS would be most of size V. Also, we will have E edges that can become saturated. And every edge, so every edge can be saturated at most V times because of what I said. It can be saturated only if we see it further than we've seen it before. Yes, so the distance increases and it cannot be more than V. So we have higher bound of V multiplied E, and each step of BFS takes also E time. So we end up with complexity V E squared. But this is still not good because in big flows we can get something like this. This is bad. Yeah, so we can consider the second optimization called Dennett's algorithm. So what Dennett's algorithm does? It actually deals with layered graph. So what means layered graph? So we have here our source, here we have our sink. Now let's run BFS on this graph and say that layer is the set of vertices in graph that are having their distance from B to S equal. Yeah, so we'll have here a layer of vertices with distance 1, layer of vertices with distance 2, and so on. Yeah. So let's at first find this layerization, and then for each step, leave only those edges in the network that are going from one layer to the next one. Yeah. So here we will end up with directed acyclic graph. So we won't have any cycles, and we won't need to deal with those revert edges and pushing flow in revert, because we won't have such situations, because we don't have cycles. Yeah. Yes. So actually, what we can do after we did this, we can just do stupid DFS on this network and push max flow in this network. Yeah, and we'll end up with some new network that we can layer once again. And what we should consider that when we pushed all this flow, we had our distance to T. Yeah? And after we push this flow, we will have this distance increased. Yeah, because if we had some extra way from S to T with lengths of dt where we can push a flow, then we'll always be done with it at this step. Yeah. So at the next step, we will have at least +1 layer. So each step works for basically BFS plus DFS time. That is a week of V plus E. Yeah, and we have no. I was wrong.
Стас, тут погано видно. Давай попробуємо в пейнті. Нет?
No.
Хорошо. Давай приділимося так, щоб було добре видно, люди тебе розуміли.
Ну, типа, я не справлюсь, типа, буде.
Борик скинув рисовалку. Ну, вона вроді би нормальна.
А ти справишся на рисунку?
Якщо я буду рисувати, ти будеш пояснювати норму?
Так.
Ну, давай. Ти будеш питатися об'яснити мені, що треба рисувати.
Давай тільки це говорити.
Добре. Вибачте, будь ласка, за погану якість відео.
Yeah, so it's like, so each step, we can consider like the same logic as we did in the previous algorithm. So each edge should be separated not more than V times. So each step will work in V multiplied E. And we won't have more than V steps because after each step, the distance between S and T is increased. So, and it cannot increase more than, so the chaining graph can't be more than V. Yes, so we'll have at most V iterations of Dennett's algorithm. And that leads to complexity of v squared multiplied e. Yeah. So that's it about sample optimizations. So let's move to some variations of max flow problem.
We cannot hear you.
Oh, sorry, we have like some problems. Yeah, so basically here we have multi-source, multi-sink problem. We have a network with basically with multiple sources and multiple sinks. Yeah, and the solution for this problem is to add a fictive sink and fictive source with all edges from the source coming to real sources and having capacity of infinity. And also all the edges from the real sinks coming to the fictive sink with also with the capacity of infinity. So yeah, why this is correct is, I think, pretty obvious. So yeah, we won't violate any previous conditions, and we won't decrease our flow because all the edges we just added, they have the capacity of infinity. So we can just push our arbitrary flow through them. Yeah, and yeah, so we won't decrease our value and we won't increase our value and violate any conditions because we just don't tamper with the inner structure of network. We just add an additional layer outside, an additional layer outside from the left, and an additional layer outside from the right. Yeah, so yeah, that's it. So the next variation is a network when we have capacities not only at edges, but we additionally have capacities on the vertices. Yeah, so for each vertex, we just say that we have some capacity W, and we can't push more flow than W through this vertex. Yeah, what's the way of solving this problem? So the algorithms we've seen before, they only dealt with edges capacity. So we want to reconstruct this graph in such way that we will still only have capacity on edges. So let's split each vertex into two. Like for vertex V, we'll have a new vertex V minus and V plus. Yeah, now let's say that all edges that were coming to V will now come to V minus, and all edges that were coming from V will be coming from V plus. Yeah, and also we add a directed edge from V minus to V plus with a capacity of W, the same as was the capacity of the vertex. Yeah. So basically, what we have now is the same graph, but we just show the inner capacity of vertex as an additional pipe or edge that flow must take from coming in the vertex and before coming out of the vertex. Yes, so it's like it's intentionally right, yeah, and yeah, and we'll never violate our conditions, and we basically didn't touch the edge structure of network at all. So we only dealt with vertices, and yeah, so the complexity will grow a little because we'll have number of our vertices multiplied by 2. But it's only a constant, so we're good, and we still have a complexity of V squared multiplied E. Yeah, so the third variation, basically in this variation, we won't be finding a max flow. We will only say whether there is a feasible flow or not. So this variation is when we have the capacity constraints not only from the top, but we'll also have lower bounds for each edge. Yeah, so how to solve this is not as trivial as previous two problems. So we want to add a new fictive sink and fictive source. Let's say it's like, yeah, a star or something, D star or something, yeah. Yeah, and now let's consider each edge with bottom constraint. So like we only consider edges with bottom constraint not being 0 now. Yeah, so let's consider this edge and assign its capacity being its top bound minus lower bound. So Q minus R. Yeah, so we have now our capacity set as minus lower bound, and also add two new edges. So the first edge that we add from new fictive source to the end of the edge in network that we're now looking at. And we'll set a capacity of this edge being the lower bound. And we won't have any lower constraints on it. And also we will have an edge from the beginning of this edge to the sink, to the new sink. Also with the capacity of lower bound. Also, we should add an edge from the old sink to the old source with a capacity of infinity. Yeah, now let's see what we just achieved. So now if we do max flow in this graph, and we'll see that max flow is equal to sum of lower bounds, then we actually find some flow that not violates our conditions. Why is it? So actually we found something called a flow of circulation. And why we found it? It's because in this graph we basically promised that we already pushed at least lower bound through the edge, because we pushed this lower bound to the end of the edge directly from new source. Also, we promised that we pushed at least lower bound at the beginning of our edge, because we pushed it from the beginning to the new sink. Yeah, and so basically, we showed that we have a flow configuration where we pushed that we had at least lower bound at the beginning of the edge and at least lower bound at the end of the edge. So we pushed this lower bound through this edge in the original network. So the outcome of this problem is, if our max flow found is equal to the sum of lower bounds, then we have feasible flow in the original network, and we don't have it in the other way. Yeah, so let's move to the next problem, being, I believe, the hardest one of all that we'll cover today. Let's assume that we want to find a max flow between every pair of vertices in the graph. Also, for the sake of this problem, we consider the network unoriented. Yeah. So, what's the simplest way of doing it? The simplest way is just to iterate over all the pairs of vertices and run a simple max flow for each pair. This will take v squared iterations of max flow. So in the worst case, we'll end up with something like O of V in force power multiplied by E. And that's kind of bad force power. Force power. Yeah. So we'll now we'll now cover the algorithm called Gomerich-Hu algorithm. and we'll need to consider two more concepts. So the first concept that we'll cover is let's watch at the max flow from I to K. Yeah. Now we can show that this flow is not least that minimum of flows from I to K and from K to J for like each ijk. Yep. Why is it? Let's just watch what is exactly a max flow from I to J. It is a value of min cards from I to J. Yeah. So consider we our min cards divided our network to the x and x tilde, and in this case we'll have either k being in x or k being in x tilde. Yeah, so if k is in x, then we'll have that min card between k and j is not bigger than min card between I and j, because I and k actually in the one set, or in this picture we'll have k and j in one set, and that means that min card between k and I is not bigger than min card between I and j. Yeah, so that means that flow between I and j is not less than flow between I and k, or flow between k and j. Yes, so now we can improve this inequality to not to have just one intermediate vertex k, but to have a sequence of intermediate vertices. So it's the same logic that Fij is bigger than minimum of Fik1, Fk1, K2, and so on, to Fk and J. Okay. Now let's consider a hypothetical complete graph on the vertices of our original network, but with every edge value to be set to a value of Fij. So every edge value in this hypothetical graph is a value of max flow between two vertices that this edge is connected. Yeah, so now let's take a look at thing called largest spanning tree. Largest spanning tree is basically like the smallest spanning tree, but largest. Yeah. So we find it the same way, just sorting edges in the reverse order. So let's look at the Fij. So what we have? We have between ij in this tree, we have some chain, yeah. And let's look at the edge Fij. So assume that Fij is bigger than every element in the chain in the tree. What does it mean? It means that we ended up with a cycle in the tree where Fij is the biggest edge. So we can just drop some edge that was in tree and replace it with Fij. So we'll end up with Fij being in the tree. Yeah. In the other way, we'll have, so now we have that if Fij is not in the tree, then it's less or equal than minimum value on the tree chain between I and j. But we proved before that Fij is not less than any of these edges. Yeah. So now we have that Fij is exactly minimum between is exactly minimum on the path from I to j in constructed tree. So we end up with a tree that is flow equivalent to our original network. What does it mean? It means that for every pair of vertices I and j, we'll have a flow in the tree exactly the same as a max flow in the original network. Yeah, so our goal is to efficiently construct this tree. How do we do this? So let's just do this. So at first, we'll be constructing this tree incrementally. And let's consider that each vertex in this tree is a set of vertices from the original network. Yeah, I'll be calling these three vertices as T vertices and vertices from an original network as G vertices. Yeah, so at first we'll have only one T vertex. That is a set of all vertices in the original network. Yes, so we'll have T vertex S1 being equal to the set E. Now, what we'll be doing for each step, we'll find in the set of T vertices, we'll find T vertex, arbitrary T vertex with more than one G vertex inside. Yes, so we want to find some S star with more than one vertex. And what should we do now? Now we can just take arbitrary two G vertices from this S star and find a min cut for them in G. Yes, so let's say that we found a min cut for x and x tilde. And now we'll use a theorem of Gomory and Hu, which I won't be proving today, but you can find its proof like in the original paper of Gomory and Hu. So the theorem says that if we had a min cut between vertices S and T, and it was like from X and X tilde, then if we take arbitrary two vertices from one of the sides, then the min cut for these vertices will be the same. So yes, so not the same, but we'll see that if we have A from X and B from X. Yes, so we have the vertices A and B from the one side of cut. Then the whole other side of cut will be in the one of the sides of new cut. Let's say that new min cut for A and B is cut from Y to Y tilde. Yep, that's Y to Y tilde. And then we'll have that the whole X tilde will lay either inside of Y or inside of Y tilde. Yep, so that's called theorem of condensation. It also allows us to find min cuts incrementally more efficient. So when we find min cut for xi and xj on the previous step, we can condensate all the other vertices of T into one vertex. Because basically every vertex of T is an intersection of some of the previous cuts. Yeah. So it will speed up our execution, but not for like incredible amount of time. But this could be worth. Yeah, but let's move on. So now we'll want to replace our vertex S star with two new vertices. So the first vertex will be S star intersected with X. So that's like all vertices from S star in the one side of the cut, and all vertices from S star in the other side of the cut. And as we said before, all our T vertices is a combination, intersection, or so of some cuts. So we'll have a property that all edges, that all vertices from each Si, being like the rest of T vertices in the tree, they will lay either in X or X tilde, and we'll want to add respectful edges from Si to X or from Si to X tilde, like to the one of the two new vertices. Yeah, and that's basically the whole algorithm. So at each step, we'll add one new vertex. So the algorithm takes exactly n steps, like v steps, sorry. Yeah, and we'll have, for each step, we'll have one iteration of min cut problem. We can solve it with max flow, and we show that we can solve max flow with v squared e. Yes, so the complete complexity will be v to the third power multiplied by e, and that's better than the naive solution. but actually it can be improved using the condensation. Yes, so I can send you over some papers to read at home about this problem and more efficient solutions. Yeah, so if you want, just reach me somewhere in Telegram or whatsoever. Yes, so, and the last topic that we're going to cover is min-cost max flow. I believe like the most of you knew what min-cost max flow does, but yeah, let's take a look. So in this simple flow problem, we have only capacities, but in min-cost max flow problem, we have also a cost of pushing flow through the edge. Like we have a cost for each particle of flow. Yeah, for each flow unit. So
Questions in the chat.
Can you repeat, please?
There are some questions in the chat.
So the question from Matli is how we create edges in problem with lower bounds. Yes. So how we do this? We add a fictive sink and fictive source, and we're adding edges from the fictive source to the end of bounded edges with a capacity of lower bound. And also we're adding edges from the start of bounded edges to the fictive sink. And also we add an edge from the original sink to original source with the capacity of infinity, just to have our circulation flow circulated. Just to revert the this one.
Yeah, sorry.
So that should be it. Yeah, and we don't bother with edges that don't have lower bound, because we'll end up with edges of capacity of 0. So we don't want to add them. It is just an overkill. Is the answer okay? Yeah, cool. So what are we doing next? Yeah, min-cost max flow. So we have a cost of pushing a unit flow, flow unit through the edge. So basically, we have pretty much the same problem, and we will be using pretty much the same approach. So in the regular max flow problem, we had a revert edges with 0 starting capacity, and we were increasing their capacity. And here we also will have revert edges with 0 starting capacity, but we'll also have a cost of this revert edges, being negated cost of the direct edges. So yeah, it's like intuitively, it's like when you're pushing flow back, then you're taking back your money that you paid for pushing it front. Yes, so the basic algorithm of finding min cost max flow is deleting negative cycles from the graph. Yeah, we can find negative cycles using Ford-Bellman algorithm. So what do? We find a negative cycle with Ford-Bellman, and then we're pushing the flow through this cycle. Yeah, and it has some capacity, so we'll push it like once and delete this cycle from the network. Yeah, so basically that's it. So we are doing the same approach as we've done before, like in Edmund's car, but instead of BFS, we are using Ford-Bellman, and that's where the increase in complexity hides, because Ford-Bellman is n squared, and BFS is like V plus E. Yeah, but we can use more efficient algorithm.
I can try to prove why we need to delete negative cycles. Okay.
Yeah, let's do it.
I will try. I'm not sure that I will succeed. Let's prove the theorem that if we don't have a cycle with negative cost in such graph that we construct, where we have simple edges and reverse edges, then we achieve the best, the minimum cost in this graph. Firstly, let's suppose that if we have at least one negative cycle, it means like we have direct edge here, then we have direct edge here, then we have some reverse edge here and direct edge here, and here is capacity like C1, here is C2, here is C3, and here is minus C4. If C1 plus C2 plus C3 minus C4 is less than 0, and for every direct edge we can increase its flow. So suppose the maximum flow through this edge is 4, but we already take 3, and for every indirect edge we have some flow, so we can delete it. For example, we already pass 1 here, so we can pass it in the other side. Then we can go through this cycle, and our cost will change to this value. So it will become less. So if we have at least one cycle, sum of the costs of which is negative, then we can make our answer better, because if we pass pass a flow through this cycle, then we didn't change the flow in the whole graph, but we make the cost better. Now let's prove that if we don't have such cycles, then we find the correct answer. Suppose that we have 2 flows, some flow C and some other flow C0. So in flow C, we don't have cycles through which we can pass at least some number of flow, and the cycle is negative. And cost of C is greater than cost of C0. We want to prove that the situation is impossible. Firstly, every flow we can split into the some ways and into the some cycles. So if we have a graph with flow, then we can take this flow like a sum of some ways from S to T, like this way plus this way, and some cycles inside of this graph, for example, like this cycle. And number of waves from S to T is equals to the flow that we pass through this graph. Now we can take C and subtract from it C0. And we will get some C1. So C1 is also be the flow, because for every node, the amount of flows that go into it will be equal to number of flows that go out of it. This is true for C. This is true for C0. So this should be true also for C1. Also in C1, the number of flow from S to T is equals to 0. Because we tell that C and C0 is both has max cost, max flow. So if we subtract, we will get the flow with 0 capacity, but with some cost because we have cycles. So C1 can be divided into the cycles without any ways. Now we can tell that C is equals to C0 plus these cycles. But we tell that every cycle in C has a positive cost. So all these numbers are positive. Not positive, but not greater than, not negative. So we can tell that C is at least as big as C0. So we prove that that if we don't have negative cycles, then we find the answer. At the first, I tell that every flow can be split into the ways and into the cycles. I can also prove this. Suppose we have some flow in the graph. we can, let's split every edge to the several edges by the number of flow we passed through it. So for example, here we pass 2. So we will create here 2 edges. And here we pass 2. So we can create here 2 edges. And let's correct if we pass the flow of amount v, then let's create v edges from t to s. For example, here we pass the flow of 3, so we will create 3 edges. In this graph, the number of edges that go into vertex is equal number of edges that go out of vertex. So in this graph exists the Euler cycle, which can start, for example, in S, goes through all edges, and then return to the S. Let's now delete this 3 edges from that Euler cycle, and we will get exactly 3 not simple ways. For example, we have some ways that go some edges, some other way, and some third way. Now we can delete cycles from these ways, and we will get some number of cycles and exactly the number of flow amount of ways without cycles. Okay, now I will. Here is some problem, some questions. About lower bound, I can try to explain it.
So basically, we want to have a circulation in graph. So we promise that we'll push something to the end of our bounded edge, and we promise that we'll push something from the start of our bounded edge. But we know that after we pushed from the start, we will get to the same. So we'll not get further. And we cannot get before we push from the source. Yes, so we just want to have like sort of connection between the end of our bounded edges and the start of our bounded edges. Yeah, and we just don't care about what exactly is this connection. Yes, so we have like consider this as we split the graph by our bounded edge and reverted the right part of it, like it's.
Can you draw the graph for our example that we write?
For the example with,
I will draw it
from the chat. An example in the chat.
yeah.
Okay, so So what we will do here, we will create the here will be 5. Yeah. Here will be 5. Oh. Yeah. Then
There will be 0.
Here will be 0. And here will be infinite. And we can pass the flow through this cycle. Here, 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 and here.
So the start t is not our through in the result.
So we want to check if we can create at least one flow with all.
Yes, so we can't find the value of max flow in this network. We can only check whether we have some feasible flows that not violate any constraints.
Yeah, and for this graph, this physical flow exists because we can like pass a flow of 5 from S to T. For example, suppose we created this flow, then we can like tell that we will through this edge we will pass the value that we pass here. So we will add this to here. Here will be 5, and we can delete this these vertices. Yeah.
So we'll find some flow this way. Actually, it will be like the minimal flow that's not violating constraints. But we can't find the maximum.
Okay, some questions? We
Yes.
can't start earlier because some teams will they live in dormitory and they need to take their like things from dormitory, and Alexander Volodymyrovich asked us to start at 11. So sorry.
Yes, so like the last thing I wanted to discuss today is how to solve min cost max flow more efficiently. That can be done with Dijkstra's algorithm. Yeah, but the issue with Dijkstra's algorithm is that this it doesn't work well with negative cycles. So we want to have a graph that will take the same properties as an original graph. So it will have the same in cost max flow as the original graph, but there won't be negative cycles. Yeah. So let's do a hack. Let's use this thing that's called Johnson's potentials. Yeah, let's assign a potential to each vertex and define a new weight of the edge as yeah, let's define it as weight potential weight of the edge from U to V. Is the actual weight of this edge plus the potential of the starting point minus the potential of the ending point. Yes, so now let's define a potential as a distance from the source to the vertex. Yeah. So initially we can find these distances with Ford-Bellman, like for the V squared for the first iteration. Yeah. So now we can use Dijkstra's algorithm to find the minimal cost augmenting chain. Yeah. So let's say that we found it, yeah. And now let's cover the properties of this chain. So we'll have that sum of weights of this of edges in the chain is basically a distance from S to D. Yeah, so but now let's watch at the sum of potential weights. Yeah, so the sum of potential weights will have like all the potentials compensate each other except of potential of source and potential of sink. So in general, we'll have that sum of potential weights at the augmenting chain is potential of source plus the distance from from source to sink minus the potential of sink. But also from our definition, we have that potential of sink is distance from source to sink. Yes, that's how we define potential. So we have that that this sum is equal to 0. Also, we're using these potentials to have all potential edges be not lower than 0. So here we have something like induction. So assume that all our edges are not lower than 0. So in this case, we'll have that this sum is exactly 0 because potential of source is 0 because the distance from source to source is 0. The potential of sink is equal to the distance from source to sink. Yeah, so this sum is 0. So each weighted potential of edges at this chain is also 0. So we proved that at this point we had all the weighted edges equal to 0. Yeah, or more than 0 if they are not lying at the augmenting chain. Yes, so we can use Dijkstra on potential weights, and that will work for V log V for iteration. But now after we did this, we can have some of our potentials broken because we pushed some flow, and that means that distances changed. But what we can do now is we can say that new potential has been increased by the value of new distance to each vertex from the source. New distance with weighted potentials, yeah. So that's the way how we recalculate the potentials. Yeah. Basically, that's all. Can you please write down the formula? Yeah. This one. Yes, so we are just increasing the potential by the value of new distance from source to the vertex. And because we are accumulating this potential, and our first property of potential being the actual distance from the source to the vertex is being held. Yeah, so this algorithm works for v log v for iteration instead of v squared for problem. Any questions? Oh, yeah, I see another question for the lower bound problem, yeah?
Yes.
Yes, new singing source are the same, and we are looking for a flow from new source to new sing. Yeah, so if you don't have any questions, I think that's all for the lecture. Yeah, so we'll thank you all. Looking forward to meet you at the contest.
Contest will start in a half of hour, exactly at 11, so you will have some of free time. Enjoy it.
Yeah, Matvey, for your question, it's about lower bound problem, yeah. So as I said, it will be the minimum flow actually. So the problem that we were solving is the problem whether the feasible flow exists, and we found a minimal one. So with this algorithm, we can't find the maximum, but maybe we can do some adjustments after that. So thank you all. See you at the contest. Reach me or Archie out in the Telegram if you have more questions. Yeah, thank you. Bye.
Bye.